This is your presenter, Asloob Mudassar, and I am presenting slide number 13A of the course on atomic and molecular physics. In the today's lecture and in some other lectures, I shall be presenting the cases when the atoms are placed in an external magnetic field. So this is the first lecture of that series. And all these lectures in which the atoms are subjected to external magnetic field will be covered under the slide 13. So the next lecture, for example, will be 13B and then 13C and then 13D, etc. So this is the first lecture, and the topics that will be covered in the today's lecture are the electron spin resonance, measurement of electron spin resonance, measurement of gyromagnetic ratio of a given sample. Atoms in a magnetic field. Directional quantization in a magnetic field. We have discussed some of the directional quantization of the magnetic field in the previous series of lectures, that is in slides number 12. Now we are going to proceed further in this direction. So directional quantization in the magnetic field. In the presence of applied magnetic field B naught, the angular momentum vectors in atoms orient themselves in certain directions relative to B naught, where B naught is called the quantization axis, in which case the directional quantization is described by the magnetic quantum number M. So you see that we have seen previously that when an atom is placed in a magnetic field, the magnetic moment of the atom starts precessional motion about the magnetic field B naught. And we have discussed different cases. For example, we have discussed pure spin magnetism. We have discussed pure orbital magnetism, and we have discussed the mixed case in which both the spin magnetism and the orbital magnetism were present. And under the applied magnetic field, we have seen that the magnetic moments of either the spin magnetic moment or the orbital magnetic moment, or in case of a mixed case where the total spin magnetic moment mu j of the atom will start its precessional motion about the magnetic field B naught. And you see that here I am not talking about a particular case. That's why I am keeping the magnetic quantum number M in a general case. In a pure spin orbital case, this M, which is the spin magnetic quantum number, will be referred to as the spin magnetic quantum number with the subscript S. So there we shall call it as MS as the spin magnetic quantum number. And in the pure orbital case, this magnetic quantum number will be referred to as ML, where ML will stand as the orbital magnetic quantum number. And if we have a mixed case in which both the spin magnetic moment and the orbital magnetic moment are present, then then this quantum number M will be referred to as Mj, where Mj will be actually the total magnetic quantum number of the atom. In the today's lecture, I shall be talking about Mj, which is the total magnetic quantum number of the atom. But so far, I am keeping this quantity in a general form, that is without any label. That is, I am not putting the label for S, the label for capital L, or the label for capital J. So this M could stand for any of these cases, provided we are discussing the pure orbital case, the pure spin magnetic case, or the mixed case in which both the spin and the orbital quantities are present, that is the spin magnetic moment and the spin and the orbital magnetic moment are present, which will add together vectorially to give you the total magnetic moment mu j of the atom, and the corresponding quantum number will be mu j as the magnetic quantum number of the atom or the electron. The interaction energy between B naught and the magnetic moment mu of the electron leads to a splitting of energy terms described by the magnetic quantum number M. So you see that in any case, that is in the case of either pure spin magnetism or the case of a pure orbital magnetism or the mixed case in which both the spin magnetism and the orbital magnetism are present. And if you apply the magnetic field B naught, then what will happen? The magnetic moment mu of the electron leads to a splitting, that is the interaction between B naught and mu will leads to the splitting of energy terms described by the magnetic quantum number m. The splitting of atomic beam in a non-uniform magnetic field for the determination of a magnetic moment mu of the atoms was performed by Stern and Gerlach experiment, and this experiment is what we have discussed in one of the previous slides. Some more experiments will be discussed in this and in the coming lectures. So in the today's lecture, I shall be talking about the electron spin resonance. The electron spin resonance, abbreviated as ESR method, involves the production of transitions between energy states of the electrons, which are characterized by different values of the magnetic quantum number m. So you see that when we apply the magnetic field, what will happen? We have electrons we have electron energies in different states corresponding to different values of a magnetic quantum number, and the transitions between those states will be referred to as the electron spin resonance. You know that in the absence of the external magnetic field, we have the levels which are determined by the quantum number J of the atom. And you know that when we have the quantum number J of the atom, it means that we have the mixed case, that is both spin magnetism and the orbital magnetism are present, and the total magnetism will be referred to as mu J, that is the J magnetic moment or the total magnetic moment of the atom. And in that case, we also talk about the total angular momentum of the atom, which is referred to as the J vector. And you know that those states are also determined by the quantum number, and which we call as total quantum number J of the atom. So you see that when there is no magnetic field, then we have the states which are determined by the quantum number J. But if you apply the magnetic field, what will happen? This J, that is the states with the quantum number J, are split into Mj states. And Mj, you know that we have discussed earlier that Mj will be 0, plus minus 1, plus minus 2, up to plus minus J. And these will be the magnetic quantum numbers in the presence of the applied magnetic field. So you see that in the presence of the applied magnetic field, the J degeneracy is lifted. That is, the level J will split into Mj levels. This is called the lifting of J degeneracy. And this is only in the presence of the applied magnetic field. So the J degeneracy is lifted by the application of an external uniform magnetic field. Transition frequencies are in the range of microwaves. That is when there is a transition between different electronic states depending upon mj values, that is transitions between different mj states, where mj is the total magnetic quantum number of the atom. Then the wavelengths or the frequencies which are emitted are in the range of microwaves, and depends on the strength. The transition frequencies are in the range of microwaves and depends on the strength of the applied magnetic field. So if the strength of the applied magnetic field is greater, then there will be a more splitting, that is, there will be a larger splitting between the mj states. So you see that the splitting between the mj states can be controlled by the application of the external magnetic field. So the transition frequencies in the range of microwaves and depends on the strength of the magnetic field. Transition between states with the different M can be observed. So you see that if you increase the value of the external magnetic field B naught, then of course the different mj levels, the splitting between different mj levels will increase. And if you reduce the external magnetic field, then the separation between mj levels will decrease. So we can control the emission of the transition in the different frequencies ranges of microwaves depending upon the application or the strength of the applied magnetic field B naught. In the Zeeman spectroscopy, which we shall discuss later, in the Zeeman spectroscopy, transitions in optical regions are observed under the effect of a magnetic field. So Zeeman effect will be discussed in the next slide. So you see that here I am presenting this picture in the considering that only pure spin magnetism is present. So in the case of pure spin magnetism, I shall be talking about S vector, which is the spin angular momentum, and the mu s, which is the spin magnetic momentum. So S and mu s, which are respectively the spin angular momentum and the spin magnetic moment of an electron or of the atom, have two orientations in the applied magnetic field. And correspondingly, there are two values of the magnetic potential energy. So in one of the previous lectures, I have discussed the spin magnetic moment mu s in vectorial form, which is given here in equation number 13.1. So mu s is equal to minus gs times mu b times vector s over h bar. On the left hand side, we have the vector mu s, which is the spin magnetic moment. On the right hand side, we have the vector s, which is the spin angular momentum. And here I am going to discuss the pure spin magnetism. That is, the orbital magnetism is not present. Only pure spin magnetism is present. And I have written down the relationship in equation number 13 point between the vectorial form of the spin magnetic moment and the spin angular momentum. And in equation number 13.2, I have given a relationship with the relationship giving you the magnitude of the spin angular momentum on the left hand side, which is related with the spin quantum number s on the right hand side. And under this square root, we have s into s plus 1, where s is the spin quantum number, and outside that one I have h bar, which is the reduced Planck's constant. So equation number 13.2 gives you the relationship between the spin angular momentum of the electron related with the spin quantum number of the electron s. And you know that for the case of a single electron, s has only one value, that is s is equal to half. So now I am going to take the magnitude, I am going to represent the spin magnetic moment in magnitude form as shown in equation number 13.3. For that one, I am going to take the magnitude of equation number 13.1, and then I am going to plug in the value of spin angular momentum, the magnitude of the spin angular momentum from equation number 13.2 into equation number 13.1, and then I am going to obtain equation number 13.3. So 13.3 will give you the magnitude of the spin angular moment, spin magnetic moment in terms of the spin angular momentum, in terms of the spin quantum number of the electron. That is mu s is equal to gs times mu b, where mu b is the Bohr magneton, and then square root of s into s plus 1. Here s is the spin quantum number, has a fixed value, s is equal to half for the case of single electron. Now you see that now I am going to apply the magnetic field, external magnetic field B naught. And for that case, I have shown the cases over here. So you see that in the picture, you can see that I have applied magnetic field B naught. The vectorial form of magnetic field B naught is given along the Z direction, which is also called the quantization direction or the Z direction. And I have shown two cases of the spin magnetic moment in the vectorial form. So you see that this spin magnetic moment, whether it is directed along the positive direction of a B naught or along the negative direction of a B naught, where I have shown both directions, then mu s will precess either along the positive direction of a B naught or along the negative direction of a B naught. And you know that mu s being a vector quantity, when it precesses about b naught, there will be three components: mu s with x component, mu s with y component, mu s with z component. Out of the two components, that is mu s x component, mu s y component, they will be averaged out to zero during the precessional motion of mu s about the magnetic field b naught, and only one component, which is the z component, will be measured, because that z component will be along the b naught directions. And you know that I have shown two values of the z component. One is minus half g into mu b, the other component along where mu s is along the negative direction and precesses along the negative b direction, will have a value which is half g into mu s. Here you can either write g or gs, because here this is the pure spin magnetism case. So you see that only Z component will survive, and we can measure, we can make some experimental arrangements in which we can measure these Z components of the spin magnetic moment mu s. Now, in order to see that how we can obtain minus half g into mu b and plus half g into mu b, this is indicated in the next two to three equations. So next what I am going to do is that I am going to take the z component of equation number 13.1. So this on the left hand side, the quantity which is the vectorial quantity mu s will be taken from will be replaced by mu s into z, mu s comma z, as shown in on the left hand side in equation number 4. So mu sz is the z component of the spin magnetic moment, as shown in equation number 4. And on the right hand side in equation number 1, this s will be represented, the z component of s will be sz. And you know that sz has values which is equal to ms into h bar. So if you put the z component, which is the sz value, and if you replace sz by its value, which is ms times h bar will be cancelled out with the h bar in the denominator, and then we will have ms only in the numerator, which I have shown in equation number 4. So mu sz is equal to minus gs into mu b into ms. And you know that ms is the spin magnetic quantum number. It means that now we have applied the magnetic field B naught to the atom, and in that case, the spin magnetic angular momentum will have the values, or will have only the sz component, and sz component has only value which is ms times h bar, and h bar will be cancelled out with the h bar in the denominator in equation number 1, and only we have ms in the numerator, which I have shown in equation number 13.4. So mu sz is equal to minus gs times mu b times ms, where ms is the spin magnetic quantum number, and it has a value of plus minus half. In the case of single electron, the value of ms will be equal to plus minus half. And due to that one, you can see that if you put the value of ms equal to plus minus half, then of course you can see that the z component, which is equal to minus half g into mu b and plus half g or gs into mu b are satisfied or are explained. So from equation, so you know that from equation number 1 to equation number 4, I have explained spin magnetic moment mu s. I have explained the magnitude of the spin angular momentum s in equation number 2, and I have given you the magnitude of the spin magnetic moment in equation number 3, and in equation number 4 I have given you the z component of the spin magnetic moment when the atom was subjected to applied magnetic field B naught. So you see that if you put the value of ms is equal to plus minus half, plus minus half in equation number 4, you will get equation number 5. So mu sz, that is the z component of the spin magnetic moment, will be equal to plus minus half times gs times mu b. And you know that when you apply external magnetic field to the atom, what will happen? There will be an interaction between the magnetic field and the spin magnetic moment. And of course, the magnetic potential energy will be stored. And that magnetic potential energy, which is Vmag is the potential energy due to the external magnetic field applied to the atom, and it is given by the interaction of the spin magnetic moment with the external magnetic field B. You can say it B or B naught. So here we have minus mu s with the dot product of B, and then we have a minus mu s into B into cos of alpha. This B can be referred to as B naught more precisely, because here we are talking about B naught. And then you can combine mu s with cos of alpha. Then this mu s cos of alpha will give you the z component of mu s, and can simply be written as mu s comma z. That is the z component of the spin magnetic moment, and then you have B as B naught. So you see that the spin, that is the magnetic potential energy mu, that is the magnetic potential energy V mag is equal to minus mu sz times B naught, as shown in equation number 13.6. The difference in magnetic potential energy in the two orientations. You see that here I have discussed the two possible orientations over here. That is the spin magnetic moment could be along the positive b direction or could be along the negative b direction, with its two orientations of the z component, one along the positive b direction and other along the negative b direction. So these two represent actually the two levels of the electron spin in the presence of the external magnetic field. So if you want to calculate the energy difference between two levels, the difference in magnetic potential energy in the two orientations is given by, as shown in equation number 13.7. That is delta E, which is the difference in magnetic potential energy in the two orientations. Delta E is equal to mod of V mag minus times the mod of V mag, that is the magnetic potential energy, which is equal to 2 times the magnitude of the V mag, and can be written as 2 times of the magnitude of the z component of the spin magnetic moment times B naught. And if you put the values of the z component of the spin magnetic moment from equation number 5 or in equation number 7, you will get final result to be equal to Gs times mu B times B naught. So this is actually the difference in magnetic potential energy of the electrons in the two orientations. That is, when you apply the magnetic field, the electron will, with the spin, will be separated into two levels, and these two levels will have energy equal to delta E. Now let us define B1 magnitude. B1 is another external magnetic field. So here we are talking about the magnitude of B1 vector, B1 magnetic field, which can be defined as the magnitude of B1 bar into sine of omega t. So V1 bar is actually the magnitude of the vector B1, and the sine of omega t is actually a sinusoidal component of that magnetic field, because the magnetic field B1 has a form which is varying sinusoidally with the frequency omega. So B1, as defined over here, is the magnetic field applied in a direction perpendicular to B naught. And this magnetic field will induce the transition if omega of the sinusoidal field satisfies the condition. Now you see that when we apply the magnetic field B naught, what will happen? There will be a splitting of the level J. and the J level degeneracy is lifted, and then we have further splitting which depends upon the total angular momentum J of the atom. J of the atom, or you can say that the total angular, that is the total quantum number J, which is the mj. So the splitting will be based on the mj values, and mj will be the total angular moment, total quantum number J of the atom. So the levels in the external field, the levels will split. As you have seen that I have shown the splitting of the levels into two levels. So these are actually the two levels. So the splitting of you can assume the dotted lines as the two levels which are splitted which are splitted when an external magnetic field is applied, and this splitting has lifted the level has lifted the J degeneracy of the atom, and then of course these levels can be governed by the magnetic quantum number mj of the atom, or simply m of the atom. Since here we are discussing only the spin, only the pure spin magnetism case, so our spin quantum number will be over spin magnetic quantum number will be ms. And ms, you know, that has only two values for the case of a single electron, which is ms is equal to plus minus half, and in the case of pure spin magnetism you see that we have only two levels separated from each other. Otherwise, in the absence of this magnetic field, external magnetic field, there will be only one level, and the orientation of mu s will also be random. So mu s is only quantized in the presence of the external magnetic field B naught. So you see that now what we are going to do is that we are going to apply another external magnetic field B naught, which is of the order, which is a which has the sinusoidal form with the frequency omega, is the magnetic field applied in a direction perpendicular to B naught, and this magnetic field will induce transition if omega of the sinusoidal field satisfies the condition, that is the energy gap delta E between the two levels will be equal to h bar omega. That is the angular frequency of the field B1 is chosen such that multiplying with h bar, it is equal to this energy difference. This will be equal to the energy difference delta E between the two levels. So this h bar omega can be written as h nu is equal to gs mu b into b naught. And you know that gs b into b, mu naught is actually the difference between these two levels. So these two levels are created in the presence of the external magnetic field B naught. Now you are applying another magnetic field B1, which is perpendicular in the direction to the external magnetic field B naught, and this magnetic field which is applied to the in a perpendicular direction to the B naught is actually a sinusoidal magnetic field having frequency omega. And if you choose the value of a frequency omega in such a way that h bar omega becomes equal to the difference difference in energy between these two levels, that is the delta E. So if you choose omega of the external magnetic field B1 in such a way that you choose omega in such a way that h bar omega is equal to delta E is equal to the difference in energy between the two states of the electron, which is equal to Gs into mu B into B naught as shown in equation number 8. Then from here you can solve this equation for the value of omega, and omega is equal to Gs into mu B over h bar multiplied with a factor B naught. This Gs mu B over h bar may be called as the gyromagnetic ratio gamma. And in this case, since this is the pure spin magnetism case, it can be represented as gamma s. So this can be represented as the spin gyromagnetic ratio. So Gs into mu b over h bar can be regarded as gamma s, or the spin gyromagnetic ratio. And this condition, which is met by changing the value of the angular frequency of the sinusoidal magnetic field B1. So when this condition is satisfied, omega is equal to Gs times mu b over h bar into B naught, then this condition is called the resonance condition. that is under this condition, what will happen? The transition will occur. So when the external magnetic field B1 will have this frequency, then the transition will occur between the two states. That is, if you apply, you can induce the transition from the higher level to the lower level, or by introducing a magnetic field B1, you can also raise this level, that is the level, lower level to the upper level. That is where these two levels are called the resonant levels. And this is also referred to as the electron spin resonance. That is, resonance means that these two levels are resonant in the sense that the frequency that you can apply the external magnetic field B1 to make this level, the upper level, to go to reduce, to decay to the level, to the lower level, or to induce to the lower level, or you can also apply the magnetic field to raise the lower level to the upper level, and the frequency and the microwaves which are emitted between these two levels can be emitted and can be reabsorbed by the sample. That is why it is called the electron spin resonance, because these two levels will be resonant levels, and since these two levels are due to pure spin magnetism case, that is why we can refer to them as the electron spin resonance case, or these two levels may be referred to as the resonant levels. So this is very important condition, that is omega is equal to Gs into mu B over H bar into B naught, as shown in equation number 9. Very important condition. So only this condition is satisfied, the transition will occur between the two spin magnet, between the two states determined, between the two states labeled with the spin magnetic quantum number Ms. And you know that Ms has only two values in our case, so only two levels are present. And if you put the values of Gs mu B over H bar in equation number 9, you will get this value as the numerical value, which is 2.8026 into 10 to the power 10 times B naught. And this will have H bar over Tesla as the unit of this quantity, because B naught is present and B naught has the value in terms of Tesla. So you see that we can vary B naught very easily under the experimental conditions from zero point 0.1 to 1 Tesla, and this will lead to frequency in the range of gigahertz, and the corresponding wavelength will be in the centimeter range. So we can talk about the centimeter waves, or we can talk about the frequency in the range of gigahertz. The allowed magnetic dipole transition belong to delta M is equal to plus minus 1. And you know that this delta M may be referred in this case, in this particular case, as delta Ms, where Ms is the spin magnetic quantum number, and delta Ms will be actually the change in the spin quantum number. And here I have dropped the subscript s over here in this equation, because this equation will be valid for the mixed case when both spin magnetism and the orbital spin magnetism are also present, will also be present. So delta M in this particular case, you can write it as delta Ms is equal to plus minus 1, or in general case, you can write it as delta M is equal to plus minus 1 when both spin magnetism and the orbital magnetism are present. Then this will be referred to as the delta Mj, where Mj will represent the total magnetic quantum number of the atom or the electron. So you see that so far I have discussed the pure spin magnetism case. But you know that in general, both spin magnetism and the orbital magnetism will be present. And in that case, we shall talk about the total magnetism of the atom. That is, we shall talk about the total angular momentum of the atom. We shall talk about the total magnetic moment of the atom, and we shall talk about the total quantum number of the atom. And in the presence of the external magnetic field, we shall also be talking about the total magnetic quantum number of the atom, Mj. So the analysis presented is for the pure spin magnetism, but it is actually extendable to the case when both orbital and the spin magnetism are present. Thus, mu s can be replaced by the total magnetic moment mu g of the atom. So for the equation number 10, which we have written as mu j is equal to mu l plus mu s. That is, we have taken the vectorial addition of the orbital magnetic moment and the spin magnetic moment as shown on the right hand side in equation number 10 to form the total magnetic moment mu j of the atom. So you see that here I am going to show you a diagram which is very similar to the case of a mechanical gyroscope. You may also consider it as a gyroscope. And you know that the gyroscope with the axle made up of bar magnet. The gray bar is actually made up of a bar magnet. And here I have applied two magnetic fields. One magnetic field is B naught, and this is generated due to electromagnet, and the coils are shown at the top and also at the bottom with the red color, and the magnetic field is also shown B naught in the form of red arrows pointing upward and downward, pointing upward and also downward. And I have also shown another magnetic field B1 with green, which was generated by electromagnets, or which was generated by the coils shown in green. And the magnetic field B naught is also directed inside. The magnetic field B naught is also directed inside. Magnetic field B1 is also directed inside. Here B1 is a uniform magnetic field where B1 can be changed, because B1 is a sinusoidal magnetic field as we have discussed earlier, and the frequency of the magnetic field B1 can also be changed. And you know that there is an angle alpha between the bar magnet with respect to the magnetic field B naught. And this bar magnet will carry out its precessional motion about the magnetic field B naught, which is also shown with the arrow over here. So this arrow shows that this magnet bar will carry out a precessional motion about the magnetic field B naught with a fixed angle alpha, provided a fixed value of a B naught B1 is used. Now changing the value of B1, we can change the value of alpha. But there should be a one condition that is required to match, and that condition is that the angular frequency omega of the magnetic field B1 should satisfy the condition given in equation number 9. That is omega, which is the angular frequency of the magnetic field B1, should be equal to Gs into mu B over H bar into B naught. So when this condition is satisfied by the magnetic field B1, then by changing the magnitude of B1, you can change the magnitude of alpha. So if B1 has a phase which coincides with the phase of this precessional motion of the bar magnet about the magnetic field B1, if the two fields are in if B1 is in phase with the precessional motion, then of course by increasing B1 you can increase the value of angle alpha, and by decreasing B1 you can decrease the angle alpha. But if B1 is in anti-phase with the precessional motion of the magnet bar about the magnetic field B, then increasing B1 you can reduce alpha, and increasing B1 you can increasing B1 you can reduce alpha, and decreasing B1 you can increase the value of alpha. So the principal rule is that when the previous condition as shown in equation number 9 is satisfied by the angular frequency omega of the field B1, then you can control the value of the angle alpha, that is the precessional angle of the field of the angle alpha of the magnet bar B about the magnetic field B can be controlled. So alpha can be controlled by B1. So here let me go through the text. Gyroscope with the axle made up of the bar magnet, and the gyroscope precesses about B naught in the presence of the gravitational field. So you see that in this case the gravitational field is also present, and we have the, in addition to that one, we have the external magnetic field P1, and our magnet bar will start its precessional motion even in the presence of the gravitational field about the magnetic field P1 B naught, and the angle alpha can be controlled by the magnitude of the magnetic field P1, provided the angular frequency omega of the field B1 satisfies the condition shown in equation number 9. Now I am going to present experiment for electron spin resonance. That is, how can we measure the electron spin resonance? And you know that when we say electron spin resonance, it means that we want to measure the separation between these two levels shown in dotted lines. And this corresponds to different values of mj values or ms values. For this pure spin magnetism case, this will correspond to ms values, as we have shown that these two levels here are ms plus minus 1, because ms will be equal to plus minus half, as you know from equation number 4. So the measurement of the separation between these two levels will be actually referred to as the measurement of spin of the electron spin resonance. So here I am going to describe the experiment for electron spin resonance. The inclination of the axis of the gyroscope relative to B naught may be changed by means of B1 if the frequency of B1 is, that is the frequency omega of the applied magnetic field B1 is equal to the precessional motion of the gyroscope. So you see that if this condition is satisfied, it means that our B1 field is now able to change the value of angle alpha. The angle of inclination alpha depends on whether B1 is in phase or out of phase with the motion of the gyroscope under the condition this. And you know that this is actually the resonance condition of the external magnetic field B1 with the precessional motion of the bar of the magnet. In 1936, Rabi measured for the first time gamma nuclei. That is, the gyromagnetic ratio of the nuclei was measured in gas atoms for the first time in 1936 by Rabi. And in 1946, Bloch and Purcell observed nuclear magnetic resonance in solid state samples. Electron spin resonance measuring apparatus. Electron spin resonance spectrometers act as standard spectroscopic accessories in many physical and chemical laboratories. For technical reasons, usually a fixed frequency is used in the spectrometer. But in this spectrometer, we have also the provision to change the fixed frequencies of the field B1. Now the sample is placed in a resonant cavity between the pole pieces of an electromagnet. This is what I am going to describe. So this is an electronics. This is our setup for the measurement of the electron spin resonance. So let me show you the full experimental setup. This is the klystron. Klystron can be used to generate microwaves of any frequency. So the klystron is a microwave generator. The microwaves will travel through the waveguide into this resonant cavity. This is the resonant cavity in which we have the sample. The sample can be placed in a resonant cavity. And you know that this sample is subject to the external magnetic field B naught. which we have applied over here. And you know that the pole pieces and the magnetic coils of this magnetic field is shown, which is surrounding the resonant cavity. It means that we are applying the magnetic field to this sample, and this sample may be a sample in the containing solid samples. And these microwaves traveling through the waveguide will illuminate the sample. And after illuminating this sample, these microwaves, after traveling through the waveguide down to the diode, will be incident on the diode, and the diode will receive the signal. This diode will display its signal on the oscilloscope. And in order to improve the sensitivity of this experimental setup, we can use a modulator. That is, we can use a modulating external magnetic field B naught. So in this experimental setup, to increase the sensitivity of the measuring field, we can make this magnetic field B naught to be a modulating magnetic field. And due to this modulation, we can improve the sensitivity. That is, we can improve the sensitivity of this diode to detect the signal. Now you see that what will happen in this setup. Microwaves will be generated, and the magnetic field is applied to the sample. So by changing the magnetic field, or by changing the magnetic field, you can change the magnetic moment of the sample. This magnetic moment of the sample in the presence of the magnetic field will carry out its precessional motion about the magnetic field. And due to the precessional motion of the magnetic field, you know that only two levels will be generated as we have discussed before. So let me show you again. These two levels, you know, that will be generated in the case of pure spin magnetism, because we are measuring the spin electron resonance. So we are assuming that our sample contains is the sample of pure spin magnetism. And when you apply the magnetic field, these two levels will be split into the sample. And over spin magnetic moment, mu s will start precessional motion about the magnetic field B naught. So in this case, our sample, the magnetic moment in our sample will carry out a precessional motion about the applied magnetic field B naught. The microwaves will be incident on the sample, so it can be absorbed by the sample. So when the microwaves when the omega of the microwaves matches with the energy separation between the two states, between the two electronic states, so when the microwave wavelength matches, when the energy of the microwaves matches with the energy gap difference between the samples between the electronic states of the sample, then of course the microwaves will be absorbed. When the microwave will be absorbed, what will happen? The signal at the diode will decrease, because the microwave reaching to the diode will decrease in strength, because some of the microwaves has been absorbed by the sample. And once the microwaves are absorbed, the sample will re-emit the same microwaves, but in different direction. But when the microwaves are emitted in a different direction, a very small portion of those microwaves emitted by the sample will reach the diode, and the other majority of the signal from the sample will be lost. And then we can observe a dip in the diode signal. This dip will indicate that the energy of the microwaves matches with the energy in the sample of this in the energy levels of this sample. So from the energy of the microwaves, we can determine the separation between energy levels of the sample. That is, we can measure the electron spin resonance. That is, we can measure the separation between the energy levels of the electron spin due to electron spin. when it is present in the applied magnetic field. So you apply the magnetic field, there will be two levels, there will be splitting of the levels in the sample, and then when the microwaves are absorbed, when the microwaves wavelength or the microwaves energy matches with the energy gap between the two levels of the sample, then of course microwaves will be absorbed, and microwaves then will reduce in its strength, and then a dip is recorded in the diode. This dip will increase, will indicate that some of the microwaves matches with the energy gap between the sample, and this will be absorbed. The microwaves will be absorbed and the dip is recorded. So by measuring the energy of the microwave, we can find out the energy gap between the two levels of the sample. So the spin resonance, electron spin resonance between the two levels of the electron can be determined very precisely by measuring the energy of the microwaves. So we can also, in this setup, we can also slightly change, precisely change the value of the magnetic field B naught, so that we can tune the energy level between the two levels of the electron spin. The spacing or the energy between the two levels of the electron spin can be precisely modified with the external magnetic field B, so that the magnetic field B should be chosen in such a way that the energy levels between the two levels of the electron spin matches exactly with the applied with the microwaves emitted by the klystron. So I think that the experimental setup is now explained. So let me go through some paragraphs. Microwaves are generated by a klystron and detected by a diode. B naught is constant, but if modulated, improves the detection sensitivity. B naught is varied to achieve resonance condition omega L. That is the precessional motion or the Larmor frequency in the sample should match this condition, which is gamma B naught. And you know that this is the resonance condition. Again, this is the resonance condition that we have spoken earlier in when we talked about equation number 9. So you can write Gs mu B over H bar can be replaced by gamma, and so omega will be equal to gamma times B naught. This is the resonance condition. And in this resonance condition means that is the energy of the microwaves matches with the energy gap between the two levels of the electron spin, the two levels of the electron which arises because of the application of the external magnetic field. So B1 is varied to achieve resonance condition, that is the omega L or the precessional frequency. Omega L is actually the precessional frequency or the Larmor frequency of the precession of the angular of the magnetic moment in the sample around the magnetic field B, and this omega L is equal to gamma times B naught. This omega L is actually, you know, that can be taken as the omega of the magnetic field B naught, which we have also applied, because the resonance condition also means that the that omega B1, that is the magnetic field, or that is the frequency of the magnetic field B1 should be equal to the Larmor frequency. So B naught is varied to achieve the resonance condition. So when this condition, that is the omega L or omega B1 or omega of the frequency of the magnetic field matches with that of gamma times B naught, where gamma is the gyromagnetic ratio, which was equal to Gs mu B over H bar, and the electron spin resonance and the electron spin resonant transitions are obtained either in absorption or emission at a wavelength of lambda is equal to 3 centimeter for this particular experimental setup, or in X band is used. So we use the microwaves with a wavelength of 3 centimeter or in X band, and we precisely tune the magnetic field B naught B1 in order that this condition of the resonance condition, that is omega L or is equal to gamma times B naught, is matched. Under this condition, the absorption will occur in the between the levels of the between the two levels, between the two resonant levels in the sample. It could be this experiment can be performed in absorption or in emission. In the absorption case, the signal in the diode will appear as a dip signal because the microwaves reaching to the diode will be reduced in strength because some of the microwaves will be absorbed by the sample and re-emitted in some other directions. Energy states of a free electron as a function of the applied magnetic field B. Energy increases in a continuous fashion. For bound electron, it will acquire discrete values. So you see that here I have shown the energy of a free electron, and you know that the energy of a free electron will increase continuously in the presence of the applied magnetic field. And you know that in the presence of the applied magnetic field, there are two levels corresponding to electron spin, which I have discussed over here again and again. I am showing you this. There are two levels. And the energy of the two levels, this is not the energy. You know that here I have shown fixed energy, shown by the dotted line or the Z component. Here the energy between the two levels is fixed. But you know that if you change the value of the magnetic field, you can change this separation shown by the dotted lines over here. So changing the strength of the magnetic field B1, you can change the separation between these two dotted lines or between the Z components of the magnetic moment in the direction of B0. So this separation, that is a separation, that is the energy of the electrons, that is the separation between the energies of the electron can be changed with the strength of the magnetic field. And you know that this energy is shown in this diagram in a continuous way. So applying B naught, you can increasing the value of B naught, you can change the separation between those two levels which I have discussed. And here I have shown a particular case with the delta is equal to 10 gigahertz, where and this corresponds to 3000 Gauss. The value of B naught is 3000 Gauss, which provides you an energy gap of delta E equal to 10 gigahertz, which matches with the energy separation between the two levels of the electron spin of the sample. And you know that here I am talking about free electron. But you know that we don't have the free electrons. The free electrons we shall only talk about the free electrons when our sample is in the form of the solid form. And the electrons are abundantly available in the solid sample. Due to in the solid sample, some of the valence electrons due to the mutual interactions will be free, will be acting as a free electrons in the solid state lying in the conduction band, and those free electrons when we apply the magnetic field, those free electrons will be varies, the energies of those free electrons will vary according to this one. And you know that this is in the form, this is under the case when we apply the external magnetic field B naught, and if you change the strength of the magnetic field B naught, the separation, energy separation between the electron spin resonance of the electron can be changed over here. And here in this particular case, with the strength of a B naught equal to 3000 Gauss, it matches with the separation of the electron spin delta E equal to 10 gigahertz, because the 10 gigahertz will then be the frequency of the microwaves. And by changing the value of B naught equal to 3000 Gauss, we have changed the separation between the levels of the spin resonance levels to match with the frequency of the microwaves to be equal to 10 gigahertz. And under this condition, the resonance will occur. That is, the sample will absorb the microwave and a dip in the diode will be recorded. So, and you know that but when we have the sample in the form of the Gaussian, but when we have a sample in the form of the gaseous form, then of course the atoms of the gas will be very much separated from each other, will be acting or will be behaving as individual atoms, and then of course this energy will follow the same trend, but it will not vary continuously, but it will vary in the form of, it will increase, but it will increase in the form of discrete values or discrete steps of energy. So for bound electron, which is only the case when the sample is in the gaseous form with a low pressure, it will acquire discrete values. That is, the energies of the electron can be changed in discrete fashion. When V naught is changed, delta E is changed. When delta E is equal to h bar omega is equal to h bar omega L, where omega is the angular frequency of the microwaves and omega L is actually the precessional frequency of the magnetic moment in the sample, and delta E is actually the energy gap between the two levels of the electron spin, between the two levels due to electron spin, due to ms is equal to plus minus half two values of the spin magnetic moment, spin angular momentum. So delta E is actually the energy gap between the two levels of the spin of the levels of the electron due to spin. So if this condition is satisfied, so when delta L becomes equal to this one, becomes equal to the energy of the incident microwave. So when this delta E becomes equal to the energy of the incident microwave, absorption takes place, and the resonance condition, that is omega L, or simply omega is equal to gamma times B naught, is the resonance condition is satisfied, which we have discussed in equation number 9 also. And a dip under this condition, a dip is observed in the signal of the diode. So you see that a constant signal is received at the diode when there is no matching of the microwave signal with the energy difference of the levels between the two. So when the microwave matches with that is when the resonance condition is satisfied. That is the frequency or the energy of the microwave satisfied with the delta E. That is the energy of the gap between the two levels, between the two resonance levels due to the spin of the electron. Then of course the absorption of the energy of the microwaves will occur, and a dip is recorded in the signal of the diode. And this particular dip, as we have demonstrated in the previous diagram, that occurs at a strength of the magnetic field equal to 3000 Gauss. And due to that one, a dip will also occur at 3000 Gauss. So this dip corresponds to the absorption of the signal of the microwave and then the energy of the microwave can be measured, and then according this dip will increase, that it is the point that we need to measure the value, that we need to measure the energy of the microwaves, and then the energy of that microwaves will be equal to the energy gap between the two levels of the electron due to spin in the presence of the magnetic field. And of course we can then measure the spin resonance measurement can be performed through this simple experimental arrangement. So at resonance, which in this particular case is B naught is equal to 3000 Gauss, absorption by the sample at lambda is equal to 3 centimeter takes place, and then re-emission at the same wavelength, that is resonance occurs. You know that resonance means that is the same wavelength is absorbed and the same wavelength is emitted. Due to the absorption at resonance, dip occurs in the signal of the diode. And you know that the resonance condition is gamma is equal to omega L over B OR. This is B naught, and we have used an additional subscript R, which stands for the resonance magnetic field B naught. So then we have H bar omega L over H bar B naught, B0 R or B naught R. Then H bar omega L can be represented by delta E, which is the optical separation between the energy levels of the two electron states in the presence of the magnetic field, in the presence of the magnetic field, and then in the denominator we have H bar into B OR or B naught R. So B naught R is the field corresponding to resonance. Delta E is determined from the resonance wavelength. That is when the when the wavelength of the microwave matches with the energy delta E. A dip is recorded, and then resonance condition is met. This is how the gyromagnetic ratio for a given sample is determined. So you see that you can determine the value of a gamma using equation number 11 through this setup. And this provides you an experimental arrangement for the measurement of the gyromagnetic ratio of a given sample using electron spin resonance. So you see that here electron spin resonance can be used to measure the gyromagnetic ratio of the given sample. Application of the electron spin resonance. So electron spin resonance measurement of gamma or G factor of the electron in ground state and in any excited state can be measured. And you know that I have demonstrated it in the today's setup. That is how we can measure the value of gamma using equation number 11. Analysis of different kinds of paramagnetic states and centers in solid state physics, etc., is possible. So we can analyze the different paramagnetic states, that is the states with different values of with the different with the presence of different values of orbital things, that is orbital magnetic moment. So if orbital magnetic moments in different concentrations are present in the sample, we have different paramagnetic states, and those different paramagnetic states can be analyzed using similar experimental setup as we have mentioned, but using electron spin resonance. Interaction of electron spin with the spins of the neighboring nuclei leads to hyperfine structure, which is the beauty of electron spin. So you see that this is also the beauty of the electron spin, that the spin of the electrons can also interact with the spin of the neighboring nuclei and lead to a structure which we call a hyperfine structure. This hyperfine structure will also be discussed in one of the lectures in future. The hyperfine splitting can help to determine the spatial distribution of the electrons in molecules, in solids, and in liquids and in solids. This lecture is continued, that is the presence of the external magnetic field to the atoms is continued to the next lecture. So far, this is the end of slide number 13A of the course on atomic and molecular physics.